Okay, today I'll be talking about 11.3, the integral test. And because I find writing and speaking at the same time pretty scary and difficult, I've written all my notes out here. And so like that way, just like easier to follow. So what is the integral test? It is used to determine if an infinite series is convergent by comparing it to an improper integral. And an improper integral is down here. It's a definite integral with infinite limits of integration. Um, and so, like for example, we see here, this is just a definite integral of f of x, but one of the integration limits is infinity, right? And so we're going to compare a series to one of these improper integrals to um, see if the series converges or diverges. Okay, and so there are a couple conditions for the initial series in order for the integral test to be valid. Otherwise, it doesn't work and like you can't use it. And so if we suppose so the suppose that like the function f is continuous, positive, and decreasing, but only on this interval here, 1 to infinity. Um, then then we can let a sub n be equal to f of n and use the integral test. And what the integral test tells us is that um, if the improper integral converges, then the series converges. If it diverges, then the series also diverges, right? And so it's not really all that complicated. It's pretty intuitive once you kind of learn how to solve it. I have two important notes listed at the bottom here. The series, let's say that the improper integral converges to 3, a finite value. That doesn't mean that the series will converge to the same value. Um, the second thing is that like the series and improper integral doesn't have to start at n equals 1. It can start at any positive integer. Um, I'll show you an example in the second practice problem, but like it's not really complicated. It's just something to keep note of. Okay. So in terms of practice problems, looking at problem one over here, um, we're going to look at the series 1 over n squared. And so the first thing we should do is that it check that it like works with all our conditions. And so I've graphed it here. Notice I've rewritten as x to the negative 2. I think that's a little bit easier for later when we do the integration. But you can see that on the area that we care about, it is continuous, positive, and decreasing, even though there's a discontinuity. There's a somewhere else in the graph, right? But that doesn't matter for what we're concerned with here. Okay, so now that we've validated that we can use the integral test, let's actually use it. Um, and the first thing that we need to do is basically use a dummy variable. So here I've used t, but you could like use any letter really. And you would write limit as the dummy variable approaches infinity. So limit as t approaches infinity of the integral of x to the negative second between 1 to t, right? And then I've like done the integration here, kept the limit, and then you plug in the bounds and get limit of t approaches infinity of this whole thing here, where negative 1 over t minus negative 1 over, or negative 1 over 1. And so essentially, as t approaches infinity for negative 1 over t, then uh, that value would go to 0, right? So here it goes to 0. So like it would be 0 minus negative 1, which is 1. And so this is a finite value, um, which then shows us that the series 1 over n squared converges, right? So in our second problem, we're going to look at whether 1 over n converges or diverges. And so again, checking the conditions here. Um, we can see that on the part of the graph we care about, which is around here, it is continuous, positive, and decreasing for like the whole time. Notice that we're going to start at n equals 2, just like in line with the note that I talked about earlier. Like it doesn't really make a difference, but I just wanted this problem to start at 2 just to show how it would work. And again, we're using the dummy variable t, limit as t approaches infinity of the integral of 1 over x between 2 to t, with respect to dx as well. And obviously the value that is ln x, and then you're going to plug in the bounds. So we get limit as t approaches infinity of ln t minus ln2. ln2 is just an integer, right? And so that's just like a finite number value. But as t approaches infinity of, or I guess, yeah, ln x, then then that then it equals infinity, right? And so infinity minus some value is still going to be infinity. Therefore, the improper integral doesn't converge to a finite value, and therefore the series 1 over x doesn't converge and therefore diverges. All right. Thank you very much. That's all I have to share for today.
Hi everyone, today we're diving into the direct comparison test. In Calculus 2, we often run into really messy series that are hard to evaluate directly, but the direct comparison test lets us determine if a series converges or diverges by comparing it to a benchmark series that we already understand. So the rules for the direct comparison test are that if series B, our benchmark series, converges, and A is less than or equal to B, then the series of A converges. But if series B diverges and A is greater than or equal to B, then the series of A diverges. So it's easy to think about it like you need a ceiling for convergence and a floor for divergence. You can also think of it like a safety net. If a bigger series converges, it forces a smaller one to converge too. If a smaller series blows up to infinity, it pushes the bigger one up with it. This might not make much sense right now, but this concept is much easier to understand through example direct comparison tests, so we'll move on to those shortly. Before we compare, we need a toolbox of series we already know the behavior of. Our best friends here are the p-series, geometric series, and harmonic series. For the p-series, remember that 1 over n is our boundary. Anything with a power larger than 1 converges. For geometric series, we just look at that common ratio r. And the harmonic series is easy because it always diverges. We'll be using these as some common benchmarks for comparison. So let's look at the first example. Suppose we have series 1 over n squared plus 5. That plus 5 makes it annoying to integrate, so let's compare it to something simpler, like 1 over n squared. We know 1 over n squared converges because it's a p-series with the p equals 2. So since our original denominator is larger, the actual fraction is smaller than our convergent benchmark. Because the ceiling converges, our series is trapped underneath it and must also converge. Now, let's use an example of divergence. So look at 1 over the square root of n minus 1. We can compare this one to 1 over the square root of n, which is a p-series where the p is 1/2. Since 1/2 is less than 1, this benchmark diverges. In our case, the minus 1 makes our denominator smaller, which actually makes our total fraction larger than the divergent benchmark. If the smaller series goes to infinity, it pushes our series to infinity too. Therefore, it diverges. Now let's look at one more example, and this one's a geometric example. So we have 3 to the n plus 2 all over n to the 1. To find the benchmark, we can ignore that plus 2 because as n increases to infinity, it's going to become insignificant anyways. So that leaves us with 3 to the n over 2 to the n, or 3 over 2 all to the power of n. This is a geometric series that grows bigger and bigger, so it diverges. Since our original series is even larger than that divergent benchmark, it definitely blows up to infinity, and it diverges by the direct comparison test. Returning once more to the DCT rules, I find it helps me to make sense of it by remembering that you need a ceiling for convergence and a floor for divergence. If you get stuck in the direct comparison test as inconclusive, like the inequality is backwards, that's a sign to try the limit comparison test instead. I will take you through the limit comparison test. If you have two series A and B with positive terms, and if the limit as n approaches infinity of series A divided by series B is a finite number C, and C is greater than zero, then either both series converge or they both diverge. So that means if A converges, B also converges. And if diverges, A will also diverge. So example one, determine if the series converges or diverges. We have n squared over n to the power 3 minus 3. So as n approaches infinity, the 3 at the bottom, at the denominator, becomes insignificant. And from that, we get series B, which will be n squared over n to the power 3, which is 1 over n. And 1 over n is a harmonic series. So harmonic series diverge. So from that, we find that the series, both A and B diverge. And if we go back to the rule of the limit as n approaches infinity, so divide uh, series A over series B, it will be n to the power 3 over 3 minus 3, which is negative 3. And negative 3 is a finite number. So both of these prove that the series diverges. Then example 2, the series 1 over 7 or n plus 1. So as n approaches infinity, the 1 in the denominator becomes insignificant. So series B becomes 1 over 7 power n, which is a geometric series with a ratio of less than 1. And that shows the series converges. If the absolute value of the ratio of R were greater than or equal 1, the series would diverge. And then if we divide series A over series B and find the limit as n approaches infinity, the limit approaches 1, which is a finite number. So from all that, the both of these metrics prove that the series converges. Then we have one with a P series. Example 3. The series 1 over n squared plus 1. As n approaches infinity, the 1 in the denominator becomes insignificant. So series B will be 1 over n squared, which is a P series. And for a P series, if the P which is 2 is greater than 1, that means the series converges. If the P were less than or equal 1, the series would diverge. And the other metric, the limit as n approaches infinity of series A over B, which is n squared over n squared plus 1. The limit is 1, which is a finite number. And so the two
bring us to the conclusion that the series converges. Yeah, that's it.